Well, thanks, Alan. My grandfather, who was a college dropout, ended up marrying my grandmother, who was 14 years younger and had a doctorate in education. So as you can imagine, he had a bit of a chip on his shoulder, and he used to introduce her by saying, this here, he was from Texas, this here is my wife, Flossie. She's a doctor, but not the kind that does anybody any good. So I'm one of those. So I was asked to talk about what will happen in the Northwest if we don't solve the climate problem. And you're going to have several speakers after me honing in on different details of what I'm going to talk about. But I wanted to sort of frame the day for you. I'm going to make reference to some peer-reviewed reports that I've been involved in. But I also want to come back a little later in the talk and focus on exactly who is we and on what time scale are we talking about. We do face a pretty significant challenge. We're on this truck here, the oil-based economy, heading down the road, and there's some wimpy little scientist there holding a stop sign saying there's a dead end ahead and a really deep ravine, and the driver says it's a hoax, dead ends don't exist. So this is one of the dynamics, is how the science is perceived, especially by folks who have a vested interest in the status quo, and some really interesting work, for example, by Naomi Oreskes exploring the political history and philosophy of that whole dimension of it. The other reality is this is happening now. This was a photo that I pulled off the Hoodoo webcam last February from the top of one of their chairlifts, and there's this paltry little patch of snow in the foreground, and as far as the eye can see, it's just brown. And you know that all too well here. You've had a few years of this down in this part of the state. A few years back, during similar conditions, heading into the Winter Olympics, Wiley, who's one of my favorite climate cartoonists, had this. I realize that the screen is too tiny for you to read this, so I'm going to read the captions to you. "Welcome to the global warming deniers' Winter Games." And even reservoirs here in normally wet Oregon were quite low. This is Detroit Lake east of Salem. And see the stranded marina there on the left. Fortunately, they got the boats out in time. It's not just here. This, I have a paper I'm about to submit probably later this week. Throughout the West, this was a really, really terrible year. So I pulled snow course records from about 600 locations where long-term snowpack has been monitored. And this was the record low at 81% of sites west of 115 degrees longitude. It was fine over in the Rockies, but the Northwest and California, it was quite bad. So these are sort of ways of framing the current conversation. We had a vivid example of a year that seems really odd. So just how bad was it? Where have we been, and where are we going? Last year, my colleague John Abatsoglu at the University of Idaho led a paper on climate trends in the Northwest. And when we set out to do this, we realized that if you want to define a regionally average temperature for the Northwest based on station observations, which are just at point locations, there are actually many different ways of coming up with a regional average. So there are 3 different data sets shown here with the colored curves indicating the sort of slower changes. And you can see they don't even agree about the slow changes. But they do all agree that it warmed over roughly the last 50 years. And we did a statistical analysis to sort out the causes and determined that the natural climate variability, which you can see is quite large, masks but does not eliminate a warming trend that can only be explained by human activity. That's another entire story about how we figured that sort of thing out. But to me, one of the interesting results from this paper was John looked at the trends in the lowest annual temperature. So if you just take each calendar year, the coldest day of the year and plot that coldest day of the year at these 100 and something stations, John found that in some places that had warmed at 10 times the rate of the average temperature. So those darkest red colors, which you see over in the colder part of the Northwest, in some cases exceed 8 degrees Celsius, so 14 or so degrees Fahrenheit. The stations down in this area that you see in the lower left, Grants Pass and Prospect are the circles. For you statisticians, that means the trends are statistically significant. Ashland and Klamath Falls are the squares a little to the right of there. So increases in the coldest temperatures and I believe Ryan is going to talk about temperature trends a little more. But I wanted to update that, so that was a graphic from a paper. This I just pulled out this morning from the NOAA. It used to be the National Climatic Data Center. Now it's the National Center for Environmental Information. And they have this cool plotting feature called Climate at a Glance, where you can make your own plots of statewide or even smaller and also regional and national temperatures. So this is the 2015 water year, October 1st to September 30th. And 2014-15 has now edged out 1933-34 as the warmest year. So we're at that data point over on the this is the downside of not using my power cord. Come on, baby. So this current year is quite a lot warmer than many years, and 34 remains the warmest year, the warmest calendar year, but we'll probably edge that out this year. And the blue curve is the long-term warming trend, which is almost 2 degrees Fahrenheit over the 120 years that we have records for. And it's a little hard to see, but there's a green curve there that's just sort of a smooth rendition of this very bumpy year-to-year ride. And you can see that most of the warming actually occurred after about the 1960s. And the reason is simply that we have ramped up fossil fuel consumption very dramatically after about World War II. Well, in some ways, you remember the Narnia book, Always Winter but Never Christmas. This year has seemed a little bit like it's always summer, and it's supposed to be, 85 again today here in mid-October. So with the bans on fireworks, I guess it's always summer but never the 4th of July or something like that. Well, just a little physics lesson here. I'm sure you're all aware of the basics of this, but the Earth gets a certain amount of energy from the sun. If you average over the whole planet and the whole year, it's 235 watts per square meter. So think about a 100-watt light bulb, and a couple of those per square meter over the whole planet. That's what the sun shines down on the top of the atmosphere. Some portion of that is absorbed by the atmosphere, some is reflected, and the net absorbed at the Earth's surface is 168 watts per square meter. If there were no, if we had an atmosphere of only nitrogen and oxygen, the warm planet would emit energy out to space in infrared wavelengths, and a temperature sufficient to emit that amount of energy would be about 0 degrees Fahrenheit. So in other words, thank God for the greenhouse effect, because otherwise there would be no life on Earth. We have these gases, which we call greenhouse gases, water vapor, carbon dioxide, methane, nitrous oxide, and they actually block that escaping heat radiation and keep the planet warmer than it would otherwise be. So that big downward pointing white arrow is the energy emitted back to Earth by the warm atmosphere dominated by those gases that I just mentioned. And so they raise the surface temperature of the Earth by about 60 degrees Fahrenheit. So raise your hand if you think we can add more greenhouse gases to the atmosphere and not warm the planet. Some warms it enough to live on, and a little more, in fact, does warm it. So this greenhouse effect is essentially the trapping of energy by certain gases in the atmosphere. It is natural, but as I'll show shortly, we have changed those gases. I mentioned at the beginning that I'll be talking about some reports that that are very important sources, and so in some slides you'll see a miniature version of the covers of one of these reports. The IPCC report, Intergovernmental Panel on Climate Change, the Working Group 1 report in 2013, that's the lower left corner. The U.S. National Climate Assessment released in May of 2014, that's the one with the kind of red U.S. map. And then Climate Change in the Northwest, published by Island Press, November 2013, and then also peer-reviewed papers. So in the IPCC report, they came up with this graphic to show global warming increases in 10-year average temperatures. The different colors are different data sets, as I showed you earlier for the Northwest. And so you see this sort of stair-stepping upward of 10-year average temperatures since the 1960s. And so the warming over the course of the 20th century is approaching 1 degree Celsius, as Bill McKibben mentioned in his opening remarks. Greenhouse gases, I mentioned, carbon dioxide, methane, and nitrous oxide shown here have gone up substantially. Carbon dioxide is approaching 400 parts per million now. These are levels not seen for millions of years. And in fact, we can only guess what they were millions of years ago using boron isotopes and science like that. We don't have any direct measurements. Methane went up more than a factor of 2, but it actually leveled off. That's the middle graph, leveled off in the late 90s and stayed flat for about 10 years before going up again. And nitrous oxide, which is produced primarily by agricultural activities, has been going up steadily as well. So all of these gases that keep us warm are getting more abundant because of human activities. If you'd rather have a cartoon than a graph to show you that, here you go. We drive, we use electricity, some of which comes from fossil sources, and agricultural activities and other practices contribute as well. Now, going into the future, thinking about a wide range of different pathways, the IPCC came up with what are called representative concentration pathways. RCP 8.5, 6.0, 4.5, and 2.6. The number indicates the number of watts per square meter of additional forcing that each would represent in the year 2100. And now these are the rates at which we're putting more CO2 into the atmosphere, not the amount of CO2 in the atmosphere. So I'll show that part on the next slide. So you have a variety of different futures to choose from, and really what this summit is about is which of these futures will we as a human race choose, and particularly here in the Rogue Basin where you're living and working. For our purposes, you will see projections for that very highest kind of scary future, RCP 8.5, and also the RCP 4.5, which starts to stabilize the climate toward the end of the century. RCP 2.6, the green one, you see emissions would have to start falling very rapidly in the 2020s and would actually have to go negative, net negative emissions by about 2070. That would be quite a feat, but that is what Bill McKibben and 350.org are aiming for. Those, as I said, those are the rates at which we're putting new carbon into the atmosphere. This is a graph that relates the cumulative emissions of carbon dioxide on the x-axis with global temperature change on the y-axis. And in the lower left corner, you see a bunch of black dots representing what actually happened. So temperature increased roughly 1 degree Celsius, as you saw. And our cumulative CO2 emissions are slightly less than 500 gigatons of carbon. Incidentally, I'm going to say a whole lot about carbon dioxide because it's the leading long-lived greenhouse gas, but as Alan and I were discussing last night at dinner, it is by no means the only important gas. So there are a lot of other things that apply to methane and nitrous oxide and so on, and we shouldn't ignore those entirely. But I like this graphic because it gives us a picture of how the past and the future are related. So the RCPs are the colored lines stretching out toward the upper right-hand corner, starting with RCP 2.6, which you can barely even see. It's the dark blue dots that end with a global temperature change of 2 degrees Celsius. And the emissions pretty much stop in about 2050, as you saw from the previous graph. Then the blue, yellow, and red are the 4.5, 6, and 8.5. And notice in particular the spacing between the dots. So with the dark blue and light blue, the dots start to get very close together as emissions approach zero. And also the temperature change grinds to a halt. But for the yellow and red, the dots actually get farther apart. So there's this sort of pell-mell hurtling toward a very hot future. And note also that they show no signs of stopping, unlike the lower two curves. So let's focus on the Northwest. What does it mean for us here? The next several graphs are almost all taken from this report. So our team used climate modeling work by about 20 different groups around the world, all of whom provide data on their simulations of the planet with RCP 4.5 and 8.5. And we've looked at the output of all those models to come up with this graphic that sort of represents the spread of possibilities from all these different modeling centers. So they also simulated the past using observed forcing. That's what's shown with the gray shading and the black curve. So an increase in temperature in the Northwest, much as observed, starting in about the 1960s. And then going forward, the difference between 4.5 and 8.5 is illustrated by the yellow shading for 4.5, the red shading for 8.5, the orange where they overlap, and then the average of all the models for each scenario is the thick line you see there. So for RCP 4.5, you see our climate starting to stabilize toward the end of this century at a regional temperature change of only 6 degrees Fahrenheit, compared with the roughly 2 degrees Fahrenheit that we've already experienced here. With 8.5, you can see it's continuing to increase, and the average of all the models is 11 degrees Fahrenheit at the end of this century. Just to put it into context, the regional average temperature departure for the Northwest from that graph I showed you earlier is about 5 degrees Fahrenheit. So this year is what we would expect would become average toward the end of the century under RCP 4.5 or much earlier under RCP 8.5. So this kind of year will happen again. It may be a few decades before it becomes the norm, but by the time this year is the norm, I hate to think what a bad year would look like. So these are really the two futures that we've sort of laid out, and of course 350.org is aiming for something even lower than what's shown here, and you know, more power to them. That would be great. For precipitation, the projections are actually sort of a wash, if you'll pardon the pun. The trends also are neither upward nor downward for our region's precipitation. And if I were to show you a map of the global projections of precipitation change, basically Canada gets wetter because as it gets warmer, the atmosphere holds more moisture, so it rains and snows harder. South of us, it gets somewhat drier, and so we're sort of caught in the middle. Some models say we'll get a little wetter, some say we'll get a little drier. The y-axis here is in percent. So the RCP 8.5 scenario has our annual average precipitation increasing about 10%. That's not really enough to notice. The Northwest's average precipitation for this last water year was 8% below average. It was drier here than for the regional average and much drier in California. But 8–10% is not something you'd really notice, and that's kind of the ballpark of what models are saying for the annual mean. Now, in writing this report, we engaged experts not just inside academia, but outside as well to sift through the long published lists of different kinds of impacts And considering both the magnitude and the consequences of these different kinds of climate impacts, we focused on, we boiled it down to 3 main climate risks. And these include both ecological, economic, and human health effects. Number 1 is the loss of snow accumulation to provide melt, which provides so much of the water in the region. The second is coastal effects, so acidification, sea level rise, inundation, coastal erosion, and so on. And the third is forest mortality and transformation. Drought affects tree survival both directly and indirectly, indirectly by increasing the risk of beetle attack and forest fire. And as a forest dies out, the trees will generally be replaced by a different mix of species just because of the way forest succession works. So these 3 are the main climate risks. There are other things as well which we covered in the report, which I'll touch on briefly. All of these have already been observed. So when we identified these as future risks, be assured that they're already underway. So as an example, this is a graph from a paper which we redrew for the National Climate Assessment for the Northwest chapter. This shows the trends in June stream flow. In a snowmelt-dominated stream, if there's less snow in a given month than there was 50 years ago, there will be less snow melt. And that's what's been happening in most of the Northwest, except for the coastal watersheds in Washington and Oregon. So all those brown dots are places where the June stream flow decreased between 1948 and 2008, in some cases by as much as 15%, the dark brown dots. Looking into the future, we can use a hydrologic model to simulate so this is for the Columbia River at the Dalles. So this is a very snowmelt-dominated basin. The x-axis goes from October to September, so that's the water year I mentioned earlier. The black is the historical, and then this is stepping forward 2020s, 2040s, and 2080s. And you can see winter flows rising and summer flows falling in the Columbia River, but it's still a snowmelt-dominated system. If you look at a more mild basin like the Yakima River, which flows into the Columbia up in central Washington, the black curve is the historical simulations. So it's got a little bit of a winter bump from rainfall before it gets too cold for rain. And then it accumulates a lot of snow, and you see that same snowmelt peak in the summer in the black curve. By the end of the century, the Yakima River becomes more like the Willamette, an almost exclusively rain-dominant river with a little bit of snow up at higher elevations. So this is an illustration of how locally dependent river flow changes can be, and of course the risks depend very much on what type of basin. Sea level rise is one of the main drivers of coastal change, and the projection for the Oregon coast, it says Newport, but it's really the whole Oregon coast, is about 24 inches over this century, but with a very wide fan of uncertainty. And this all depends on when the major subduction zone earthquake occurs. The last time this happened in January 1700, the region got about 5 feet of sea level rise in a couple of minutes. So just imagine at some point on there, the graph jumping up to the top of the diagram. We don't know whether that's going to happen in 200 years or in 3 minutes. I'm hoping for 200 years from now. Forests have already been significantly affected by some climate-driven factors. This shows in red the area burned between the mid-'80s or since about the mid-'80s. In red, this doesn't include the last couple of years, which would add a whole lot more red. But you can see the Biscuit Fire down there in the lower left. And then also insect and disease area. So most of the forest area in the Northwest, except for, again, the region west of the Cascades in the Willamette Valley and western Washington, relatively unaffected. But this year, of course, there were some forest fires in even those normally wetter forests. And we can compute the relationship between climate and area burned just from the past and project it out into the future. And so this is for a very modest 2 degrees Fahrenheit global temperature increase. And the colors indicate the change in the median area burned. And so those big red areas in the Rockies are at factor of 5 or more increase in median area burn. So a hot summer a long, hot, dry summer leads to more fires, which are of course, this year has been a good illustration of that relationship. So I've covered the 3 main risks identified in the report. I just want to briefly mention 2 other chapters that we cover, and later speakers will get into this in more detail. With agriculture, there are a number of factors, and the reason that we didn't include this as one of the 3 main risks is that some of these are positives for agriculture and some are negatives. So a longer growing season is generally a positive. There are exceptions, as Greg Jones will illustrate. Drought stress, however, is a negative. Hotter, drier summers lead to more drought stress. CO2 fertilization is a positive. Most plants grow better with more carbon dioxide. However, weeds are also plants, and they love higher CO2. In fact, they love higher CO2 much more than crop plants do in general. Some crops are very dependent on certain sequences of weather, and a crop can be ruined by rain at the wrong time or by not getting enough cold temperatures over the winter. So chilling requirements are sort of complicating factor. And then insect pests are another factor. Many insects reproduce more quickly or grow more quickly or can extend their range in warmer temperatures. We also had a chapter on tribal dimensions, and Kendra just very briefly mentioned a couple of things in her opening remarks. In this chapter, we noted that the tribal dimensions of climate change are in some ways the same and in some ways quite different from the mainstream culture. Many tribes have treaty rights that recognize their usual and accustomed areas, but the land and resources that those refer to are, in a sense, static, and there are challenges in a dynamic environment such as what we've created for ourselves. There are, in addition, unique challenges with climate change. The changing resources that I've talked about, the forests, and I didn't really talk about what lives in the forests and the rivers, but plants, animals, fish, and so on, many have a cultural or even spiritual significance for Native Americans that is much more profound than for the dominant culture. Some tribes, for example, the Swinomish tribe up in Washington, have begun work to adapt to climate change. So there are important lessons to be learned there. So I want to come back to the title of the talk, What Will Happen in the Northwest If We Don't Solve the Climate Problem? Well, as I hope I've illustrated, the challenge really is one of magnitude. We've already, to paraphrase what Bill McKibben said, we've already bought ourselves another degree of climate chaos. So the question is whether we'll stop at 1 degree, and by we, I mean the whole human race. Everybody needs to be involved, not just SOCAN, not just the state of Oregon. So I want to come back to this graph. Where do we want to end up? Do we want to go up to that right-hand corner and see what happens? Well, as I mentioned, we've burned a little less than 500, or we've put a little less than 500 gigatons of carbon into the atmosphere. Many jurisdictions, including the European Union and the state of California, led by then Governor Schwarzenegger, picked a target of 2 degrees Celsius as a limit for dangerous interference with the climate system. So achieving 2 degrees Celsius of temperature change requires limiting total emissions to about 800 or 750 gigatons of carbon, so just about twice what we've already emitted. So that means dialing back emissions just as rapidly as we're currently dialing them up. Proven reserves of fossil fuels amount to about 1,500 gigatons of carbon. So even if we stopped all exploration and just burned what we already know is there, we would easily get to 3.5 or 4 degrees Celsius of temperature change, so on the order of 7 degrees global temperature change. Well, the sad fact is that we are currently on the RCP 8.5 trajectory. So these are the emissions curves from those RCPs that I showed you earlier, and the red dots show the actual emissions, peaking there in the last year is 2012, for which data are available. This doesn't mean that we have to stay on RCP 8.5, but that's where we are now. So we have sort of a version of Pascal's wager. We can imagine 4 futures. One is that the science is right and we take action. So we avert some real climate disasters and turns out better. Another possibility is that the science is wrong and we take no action. And, well, okay, that's fine. You know, climate change turns out not to be a big deal, and we don't do anything differently with our economy or whatever, and maybe things turn out fine. Another possibility is that the science is wrong, and we take action, and it turns out that we limit our economic growth, and it drags down our GDP. Most estimates are the amount by which it would drag down our GDP would be to give us an economy on par with Switzerland. So that's what that little photo is of Switzerland. Wouldn't that be terrible? So I'll give that a frowny face because some people genuinely would be unhappy with the GDP of Switzerland. Okay, I don't really need that reminder. I need to turn off. So the fourth possibility, of course, is that, oh, sorry, we have to go back through. The fourth possibility is that the science is right, but we have not taken any action, and the scream. Last March, the US filed its intended nationally determined contribution. Each nation is allowed to sort of specify what it wants to do under international treaty about climate change, which basically means, you know, let's have a weight loss program where you can pick your own target and the target can be 0. That's really effective, right? But the US and China have a joint agreement to reduce emissions. So the US target is to reduce emissions 26 to 28% below 2005 levels by 2025. So to show you what's actually been happening, in fact, the US has turned around its emissions. This is in carbon dioxide equivalent, so it's CO2 and all the other gases. So they peaked in 2007. And are down now 11%. The last dot on there is 2012, so we don't yet know about 2013, 14, or 15. And for reference, that intended target is shown over there on the right. So most of that reduction, of course, was because of the recession. Some was because of other factors, fuel switching and so on. But we are headed in that direction. Anybody who thinks that we can just sort of coast to get to that 26 or 28% reduction is, well, let's just say maybe a little Pollyanna-ish. It will take a huge effort to get to that level. Here in Oregon, we actually peaked earlier in 1999. And emissions in Oregon are down about 16% since that peak. And you see they went down in the early 2000s and then started to creep back up, and then the recession effect kicked in. But they've continued going down even as our economy has recovered. So this is, in some ways, fairly encouraging. We're at least headed in the direction of reducing emissions, and we haven't wrecked our economy to do it. So why are emissions going up even if the US is going down? One word. China, that's right. So China sees how we're living and says, we want that too. I happened to be in Beijing for an IPCC meeting about 10 years ago, And there are all these billboards advertising subdivisions with names like Rancho Santa Fe, and they have 2-car garages. It looks like something straight out of a California suburb. So they want what we got, and who can blame them? So I want to just end on this. We really have a choice between 2 very different futures, a future in which climate challenges pop up unexpectedly or expectedly at increasingly frustrating and challenging intervals, or one where we gradually start to space those out and stabilize the climate at a more manageable level. I mentioned the 3 main risks that we've identified for the Northwest: the loss of snow, the coastal problems, and forest mortality. And in a sense, we are running out of time to avoid dangerous climate change. Hitting that 2 degrees Celsius target that many have identified would require very drastic and immediate global reductions in emissions. And I'll just end with a cartoon. What if it's a big hoax and we create a better world for nothing? Thank you.